Hello there. In this video we're going to introduce a interesting type of function known as a piecewise function. So a piecewise function is just a function with different functions glued together on different types of intervals. For example, you can have a line graph here and you can have a parabola there or something like that. So it's like line plus parabola equals piecewise function. So exactly how would you write a piecewise function algebraically? So we can start off with this graph as an example. So f of x is going to be equal to two pieces, in which we usually separate by braces. So the left piece is going to be the function y is equal to x, and the right piece is going to be equal to x squared. So this is going to be true for x less than 0, and this is going to be true for x greater than or equal to 0. Both of these curves meet at the origin, so whether you choose to put the equality sign on the x or the x squared does not matter in this case. But this is a basic example of a piecewise function. Now let's look at another function that we actually know a lot about, and that's the absolute value function. So remember the absolute value function and what it looks like. It looks like this. It looks like a V. But notice that this curve is actually the piecewise function of two functions that we know, because we know that this line in blue is y is equal to x. We also know by our transformation knowledge that this line here is y is equal to negative x. So notice that the absolute value is just a piecewise function of two curves. Y is equal to negative x on the left, and y is equal to positive x on the right. So therefore we can say that the absolute value of x is equal to the piecewise function negative x for x less than 0, and positive x for x greater than or equal to 0. Again, both of these curves meet at 0, 0, so whether you put the equality sign on the left or the right does not matter in this case. So let us look at another example where it would matter. So let us look at example 3. So let's assume h of x is defined to be equal to x squared for x less than or equal to 0, and x plus 2 for x greater than 0. So we know what x squared looks like. X squared looks like this. We also know what x plus 2 is. That's just a line shifted up 2 units. So we break this curve apart about this breakpoint. X is equal to 0. So this is going to be the left part of our graph, and this is going to be the right part of our graph. Keep in mind, there's going to be an open circle on the line and a closed circle on the graph that's dictated by these equality signs. So once we have identified those important features, then we just glue these pieces together on our graph. So our left piece is going to be here, and our right piece is going to be here. Keep in mind the open circle is dictated by the inequality signs. And here it does matter because they do not meet at the same exact point at the breakoff point for the piecewise function. So this is the graph of the relation h. Let's look at another example. So example 4. And of course you can break this into very many pieces if you truly wish. For example, let's define the function say k of x. So k of x is going to be defined to be equal to 3 pieces. X plus 1 the quantity squared for x less than negative 1. We're going to define it to be equal to negative 2 for negative 1 less than or x less than or equal to 1. And we're going to define it to be x minus 1 squared for x bigger than 1. I've carefully decided these functions so it's easy to determine where these functions break off. So let's begin by graphing each of these functions on the entire domain of each. So piece 1, piece 2, piece 3. So piece 1, x plus 1 squared, is just a parabola shifted to the left 1 unit. So this is going to be the graph of piece 1. Y is equal to negative 2 is just a horizontal line that passes through 0, negative 2, so that's the graph of piece 2. The graph of piece 3 is just a parabola shifted to the right 1 unit, so this is going to be the graph of piece 3. Now we need to figure out which part of these pieces that we want. So the breakpoint between piece 1 and piece 2 is located at x is equal to -1. So since -1 is the vertex of this, and we want that to be true for x less than -1, the piece for the parabola that we want is going to be this piece. When x is equal to -1 for the next piece, notice that that curve is going to be equal to -2 if for any value of x we choose. That's also going to be true for the other end of the domain, for which is defined to be equal to -2 anyway. So that means this interior piece is going to be the piece of the line that we want. Once that is done, we then turn to our next piece in sequence, which is going to be the next parabola. So when x is equal to 1, that's when that vertex exists, cleverly enough, and we want this to be true for x bigger than 1. So therefore we want the right side of this parabola to be part of our piecewise function. Now that we have everything organized, then we have all of the tools that we need in order to construct the graph of our piecewise function. So all you need to do is just glue together each of these pieces. So at -1 and 1 and -2, these are the main values that we need. So this is the right piece. Notice this is going to be an open circle because this is going to be less than, not less than or equal to. This is going to be an closed circle because it is less than or equal to, or x is greater than or equal to -1. And then we're going to pass through here. It's going to be a closed circle because it's x is less than or equal to -1, not less than. And this is going to be an open circle, and then it's going to go up. And why is it an open circle? Because it's greater than 1. And notice that, these two things cannot be closed simultaneously, else it's not a function of x anymore because it will fail the vertical line test. So this is the graph of our relation k. So let's do one more example just for practice. And this is going to be a function that has infinitely many pieces. So let's call this function j of x. So I'm going to define j of x in this particular way. I'm going to let it be equal to 0 if x is between 0 and 1, but equal to 0 and less than 1. I'm going to let it be equal to 1 if 1 is less than or equal to x but less than 2. Once you start hitting the values in between 2 and 3, I want it to be equal to 2. Once it hits 3, I want it to be equal to 3. So 3.2, 3.3, 3.9, all of them are going to be mapped to 3, and so on. I'm also going to do the same in the negative direction. So I'm going to let this function be equal to -1 if x is from -1 less than or equal to x less than 0. I'm going to let it be equal to -2 for -2 less than or equal to x less than -1, and so on in that direction. So all of these are horizontal lines just defined on different intervals. So if you want to try this on your own, take a minute to pause this video and see if you can graph this relation. So I'm going to begin by looking at all of my breakpoints. So notice I'm at 0 when x is equal to 0. So let's start there. So when x is equal to 0, y is equal to 0. So this point is going to be on the curve. When x is equal to 1, y is equal to 1. So that means 1, 1 is also on this curve. And you can find that this is going to be true for any value that lies on the line y is equal to x. Now let's look at this piece in detail. Notice for any x between 0 and 1, that includes 0.1, 0.2, all the way up to 0.9, it's going to be equal to 0. Not only, that's going to be true until you hit 1. So then it's going to jump here. And then it's going to be equal to 1 for all values between 1 and 2. And then once you hit 2, it's going to jump up. And then you'll eventually find out that your relation is going to look like this. So this is the graph of relation j. Some people actually refer to this function as a step function for obvious purposes. And this actually has some other usefulness, useful applications that we may discuss later. Some people even denote this using other notation that you may see from time to time. Sometimes we denote this via a bracket, and some people use this notation as well. that means round down whatever number you have. So 6.2 rounds down to 6. 6.9 rounds down to 6, and so on. And some people will use even a word called floor of x, which is just another way of saying round down, instead of round up, for example. The round up function, which some people call the ceiling function, would have a similar function to this, but instead of 0.1 going to 0, 0.1 would then go to 1. But this is just a basic overview of how you can graph piecewise functions by sort of decomposing each of the pieces and then gluing them back together at the end.